Nerd.
Hello, so welcome to the new chapter. The chapter is motion in one dimension, and we're starting with the topic rest and motion. So, in layman terms, we absolutely know what rest is and motion is, right? An object is in rest, that it's not moving, and when it's moving, it's in motion, right? But in physics terms, we can define it as rest as state of a body when the position doesn't change with time. You know, with time. This is the proper definition, okay? And motion is the same thing. The state of the body when the position changes with time. From changes, I remembered R.I.P. Ozzy anyway. Love them. So, suppose I'll just give you an example. This is a very simple example. This is a ball lying on the floor, and you're just sitting on a chair watching that ball. If it's not moving, if it's not changing its position, it's just in the same place. That is, it's in rest. And if the ball changes its place, you know that it's in motion. Now, the main thing starts here that rest and motion are not absolute. This is the important thing here. Because suppose you're sitting under a tree, this view, and you see two trains going parallelly with each other with the same speed, assume, and you see that the trains are moving in this direction, right? But a person sitting in this train will see that a person sitting in this train on this train as a whole will be in rest to him. Now, why? This is because of a concept called relative velocity. Right, well, in short. So we'll learn about this later, but just know this that rest and motion are not absolute because from one frame of reference, that is our next topic, like if the frame of reference is you, an object might be in rest or might be in motion. And if suppose the frame of reference is this, then the object may be in rest. So it all depends upon the point of view we're speaking about. We check out the frame of reference. In the simplest terms, we know that frame of reference is basically point of view. And in the last example, we saw that the rest and motion depends upon the point of view or the frame of reference. In a graphical method, we can assume that suppose there's a point A with the coordinates 5, 6. Now this is also dependent upon a frame of reference. Why? Because we assume that this origin, that is this point, 0, 0, 0 is the frame of reference because the point A, that's 5 units in x-axis and 6 units in y-axis. Right, this is what it defines. So we take this as the frame of reference and we see, suppose this is the length 5 units and this is the length 6 units in y-axis and x-axis respectively. Minus z, minus y, minus x. So this is our frame of reference, and this is like a normal convention. But you can change the frame of reference also. Suppose in this, suppose this point that is 2 units away from the origin is the frame of reference. This is the frame of reference. Okay. So the point 5, 6 will be from here. That is 5 units from here and 6 units from here. So basically the total distance from the origin here is 7. So the point of view changes the whole thing. That's what I want to say. So let's move to the next topic, that how it affects the distance and displacement. So now types of motion. So how many types of motion are there? Basically 3, but like 1D, 2D and 3D. There's some kid explaining 4D on YouTube. You don't need to get into that. So we'll start with 1D. So what is 1D? First of all, amazing band. Second is it's a motion where suppose, I mean, this is the layman term, that suppose only this axis exists. And in physics terms is where position of an object can be determined by only one axis. Suppose the car is moving in a straight line. Okay, suppose this is the car, it's moving in a straight line. So you can just suppose, and this is the x-axis, you can find its position just on the x-axis and none of the other axis. Or an apple falling from a tree, you can just find the position on the y-axis because it's changing on the y-axis only. It's not moving in the x-axis, it's just going down in the y-axis. So now 2D, where position can be found out by two axes. On with two axes. Like suppose a ball, you throw it like this with an angle theta from the horizontal. So basically it will have a vertical component v and a horizontal component x, and the motion of the ball will be like this. So the position can be, suppose it's here, it's some x and y component from the ground. That is, suppose this position is 5 meter from, suppose there's a frame of reference, so it's 5 meter from this and 5 meter in the y-axis. So this is the position. This will also have a position, suppose it's 10, 5, because it got a little lower and it got further from the origin in the x-axis. So it's just defined by two axes, that's x and y, or any other y, z, x, z. So it's 2D. 3D is just anything, suppose a ball and stuff, a real 3D ball, or any AAA games that you play. 3D is basically position found out by the axis. You guys know what 3D means, and this is the definition of it, that this ball has to have dimensions of length, breadth, and width. So it will have a, like, suppose 2, 3, 4, this kind of dimensions, like these kind of coordinates to determine its position. So this is what 3D is. We'll next move to the next topic. Now, very important. This is distance versus displacement. This is where the real chapter starts from. So distance is the length of the actual path between the initial and this is the main thing. Length of the actual path between the initial and final positions of the body is called the distance covered by the body. And the shortest distance between the initial and final positions of a body and is directed from initial to the final position. So basically, suppose I'll just take an example. A man is starting from this point. It's going, suppose, 3 meter north and it's going 4 meter east. Okay. So the distance it will travel is the actual path length, that is 3 meter plus 4 meter, that is 7 meter to reach here, obviously. Now for displacement, I'll just take the same thing, 4 meter. Now what is the initial point? This is the initial point. What is the final point? This is the final point, right? Now the distance between the initial and final point, it does not depend upon the path. The distance is 7 meter, that is 3 meter plus 4 meter, but the displacement is the distance between the shortest distance between the initial and final points. And as you can see, this is a Pythagorean triangle. You can find this easily by the Pythagoras theorem. This is the base, this is the perpendicular, and just find it by 3 square plus 4 square equal to 5 meters. So the length of this is 5 meters. So the displacement is 5 meters. Okay. Distance has no direction, no sense of direction, therefore distance is a scalar quantity. Displacement has sense of direction, obviously, because distance, you can just go from this distance to like this, and all these path lengths would be like added to get here. And displacement, suppose the same thing, this depends upon the initial and final point. And the direction. You're going from here to here, that is here to here. If you had gone from here to here, the direction of displacement changes. Hence, displacement is a vector quantity and distance is a scalar quantity. Distance of a moving body is always positive. Distance of a body can be, displacement of a body can be zero, positive or negative. And both the SI units are meter. This is very important. SI unit of both distance and disk are meter. And the point was that distance is always positive, because suppose you move from here to here to here to here anything, the path length would always be added, right? If you move from here to here, the path, there is some distance that you have covered. So distance can never be zero if you have moved. Distance can never be equal to zero if movement is there. If you're in rest completely, then distance is zero. Distance traveled is zero. Okay, but displacement, and what was displacement? That is the difference between initial and final position. So suppose you're starting from here, you went all the way around and landed here. So your initial and final positions are same. They have coincided. So the distance between them, so the distance between the initial and final position equal to zero. So the displacement equal to zero in a closed path. Suppose this is just a perfect circle, but if you go from like here to any random path, it will still be zero if the initial and final point are same, and it makes a round trip. It goes from here to here to here to here to here, but landed in the same point. Here also initial equal to final position. So displacement equal to zero. Now, distance is dependent upon the path followed by the body, and displacement is independent of the path followed. Obviously, we saw this here. The distance, you go from here to here to here to here. Suppose this is 1 meter, 2 meter, 3 meter, 4 meter. You have to add all these 1 plus 2 plus 3 plus 4. This is the total distance traveled. The path is considered. So this is 10 meter, the distance, but the displacement is just, this is the initial point, this is the final point. This will be the displacement. Any random thing, if this is the initial point, this is the final point, this will be the displacement, but distance is the whole path length combined. Okay. So that's it. We'll move to our next point. Now there's one more thing that I forgot to tell you. That is, I have shown you how the displacement can be zero. That is, if it completes a round trip in any form, it does not have to be a circle. The initial and final position have to be same. This is when the displacement is zero. But the displacement can be negative also. How? Suppose this is a plane, and this is our frame of reference. That is our zero. Suppose this direction is positive and this side it's negative. So suppose an object travels 5 meters in this direction. So we have to call it plus 5 meter displacement. If the same object or any object travels 5 meters in this direction, then the displacement is negative 5 meters. So the minus sign depicts that the side we have taken negative, the object has traveled in that direction. This is a very simple thing. This is how displacement can be negative. Now there are some important points that we have to discuss about the distance versus displacement. First of all, that we use distance and displacement in a mathematical term or like in everyday language simultaneously. So don't think of them as like different when we solve some numericals or you see some numericals. Okay, so the first point here is distance always increases with time for a moving body, and displacement may increase or decrease with time depending on the movement of the body. So basically, distance is addition of path lengths, right? So it always adds up and it increases. So it always increases, it can never decrease. But displacement, suppose this ball has moved 5 meters in this direction and it has taken a U-turn and traveled 2 meters in this direction. So basically, if this is the initial point and this is the final point, this is 5 meters, this is 2 meters. So the difference between initial and final positions will be 3 meter, right? So the displacement is 3 meter, but the distance traveled will be 5 meter in this direction and 2 meter in this direction. Whether it be round trip, it doesn't matter because the path length is 5 plus 2, that is 7 meter. So the displacement may decrease, that is 5 meter till here, and then it decreases to 3 meter when it reaches here. But the distance, it's always increasing. It's 5 meter here, so it's 7 meter here. So we'll go to the next point. That is odometer fitted in vehicles measures the distance covered by the vehicle. Measures the distance. Hence the reading on it never decreases. So obviously when distance cannot decrease, the reading on the odometer cannot be decreased because it measures the distance. Now displacement and distance, this is a very important topic. The magnitude of distance and displacement is equal when the particle moves in a straight line without reversing its direction. Now we saw when it's reversing its direction, we saw with the earlier example that the displacement is 3 meter and the distance is 7 meter. So here the displacement is not equal to distance. But suppose a ball travels from here to here and the path length is 5 meter, that is the distance is 5 meter. But the initial and final positions are this, and the distance between the initial and final position is also 5 meter, that is the displacement is also 5 meter. So an object has traveled in a straight line without reversing its direction. So in that case, distance and displacement have the same magnitude. Okay, now in other cases, this may not be true. Obviously, in cases like this, suppose in a round trip, the displacement is 0 and the distance is something, the path length is like greater than 0 at least. And in every case, you have noticed this one thing, that the distance is either equal to the displacement or it's always, or it's greater than the displacement. So there's a very important observation here that distance is always greater than equal to the displacement. So basically, if we take a ratio, then this is always true. Okay, this will be always be true. The distance can be equal to the displacement, but it will never be lesser than displacement. So if we take it in a mathematical form, suppose this is distance and this is displacement, the ratio will always be bigger than 1, and this is given in your Kaplan. Okay, because suppose it's 5/3, it's an improper ratio. It will always be greater than 1 because distance is always bigger than the displacement. And the reverse is like displacement greater than displacement by distance, it's always lesser than 1. Why? Because it's like 3/5. It will be lesser than 1, obviously. So we'll move to our next topic. Now we'll see displacement in terms of position vectors. That is, if we saw graphical representation of displacement. This is the 3D coordinate system, and this is the origin. And suppose there are 2 points A with coordinates x1, y1, and z1. Suppose this is B, x2, y2, and z2. So suppose a body is traveling from A to B. This is the displacement, right? This is A and B, the difference between the point final. This is the initial point. This is the final point. So the difference between them is the displacement. We'll call it R. Okay. So what is R? R is the difference between final and initial. And we can define this as, suppose R displacement in x direction, it's x2 minus x1. The final position is x2, the initial position is x1. Similarly, for in y-axis, this will be y2 minus y1. In z-axis, it will be z2 minus z1. So basically, the vector results in We write it in vector form because displacement is a vector. We can write it as, sorry, x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. And we know how to find out the magnitude of this vector, that is, to take the resultant, 2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. This is from our last chapter, how to find the resultant of how to find the magnitude of the resultant. And in this case, the resultant is r, and these are like the same points 2 comma 3 comma 4, but it's represented in like this manner, which makes it more complicated. When it comes to like mathematical form, you'll find it very easy. So you don't have to remember this, just understand this. I've taught you because it was given in the Kaplan. We've already discussed this somewhat. That is a sign convention. Suppose this is the plane. This is our origin, the frame of reference. We take this direction as positive. This is called the sign convention, assigning signs to specific directions. So this is positive direction, suppose. This is the negative direction. Displacement here is positive. Displacement in this direction is negative. Okay, so suppose a ball is thrown vertically upward. So it will go like this and fall like this. So suppose it has a velocity v and it also comes down with a velocity v. You'll learn this in the next chapter. But it goes on with a velocity v in this direction and comes down with a velocity v in this direction. So basically, suppose we take the upper side, the positive y-axis as positive. So this velocity is positive. And we have to take this velocity as negative because it's coming in this direction. That is opposite to the direction we took as positive. Similarly, if this is a cliff and we take this direction as positive and we throw a ball here. Same thing, we throw a ball upward and it falls in this direction. So this velocity will be v, that is plus v, and this velocity will be minus v. This will be negative because it's in this direction. Also, the gravitation that is acting in this direction will also be negative. The significance of this you'll understand in solving questions in equation of motion. You see out of the blue now, but it's just assigning directions according to the like convenience you want in a question. Just you can assign anything. It's not that this is the specific convention that you have to follow, that the upper side is positive, the lower side is negative, the left side is negative, the right side is positive. You can assign anything. So that's very simple. Let's move to the next topic. So speed and velocity. First of all, we use speed and velocity like distance and displacement in mathematical questions, that we use them simultaneously. We assume them same. But when we have to look at the differences, there comes some differences that we have to focus on. That is speed. It is amount of distance traveled in a specific time. Okay, so speed, or we can represent it with S equal to distance by time. This is the formula of speed. Okay, and distance is meter, time is in second. So the SI unit of speed is meter per second. It's the amount of distance. Whereas velocity is amount of displacement by a body in a specific time. So velocity, or V, is displacement by time. Again, displacement is also meter, time is in second. The SI unit of velocity is also meter per second. Now, speed concerns with distance. Hence, speed is scalar. Velocity deals with displacement. Hence, P is vector. We might as well write it like this. Okay, so this is basically velocity and speed. The main crux is speed deals with distance and velocity deals with displacement. Now there are two terms called average speed and average velocity. I'll explain it to you in a minute. That suppose, and this is the average sign. Okay, this is the average sign. Suppose we have to find an average of a quantity A, we'll just represent it with these two brackets. Okay, so average speed is basically total distance by total time. In average speed, average velocity, it's total displacement by total time. Okay, suppose there's a question that a body travels 30 meters in 2 seconds in the north and 40 meters in suppose 3 seconds. So what will be the speed and velocity? So the speed is distance by time. Find out the distance, that is 30 meter plus 40 meter equal to 70 meters. Right, and the time, the total time for the path taken, that is 2 seconds, and 3 seconds, that is a total of 5 seconds. So this will be 14 meter per second. And velocity equal to displacement by time, we know this. So the displacement here will be, this is the initial point, this is the final point. So the distance between them will be 50 meter. This is calculated by Pythagoras. So 50 meter by, also the time is same because it takes 5 seconds to go from here to here. The logic is same. So it's 10 meter per second. Right. Also, like distance and displacement, you'll see one thing in every sum. This is just one example that I have told you, that the magnitude of speed will always be greater or equal to the magnitude of velocity. Just the same as in distance and displacement. Speed deals with distance and velocity deals with displacement, and the order is literally the same. Why? Because suppose in a round trip, the object travels from here to here, suppose it travels 2 meters in 2 seconds. So the speed will be 2 meter by 2 seconds, that is 1 meter per second. And the velocity will be 0 because the displacement is 0 by 2 seconds, that is 0 meter per second. In any case, you'll see that speed's magnitude is greater than the magnitude of velocity. Okay. So the same thing, the numerator is bigger than the denominator. So it will be always greater than or equal to 1. When the similar thing, the distance and displacement is same. Also, we can say that the object is traveling in a straight line, because in that case, distance and displacement are same. So this is speed versus velocity. We'll move to our next topic. Just one small thing, that like distance never decreases, it always increases with time, and displacement may increase or decrease or even become 0. Similarly, speed as it deals with distance always increases, and velocity may increase or decrease. That's it. Now we start with conversion of units. Suppose for our convenience, one quantity is given in a question that's in meter per second, and another quantity is given in kilometer per hour or kilometer per second, anything like that. So we have to convert it into one unit. Suppose we'll convert everything into meter per second or meter, like the SI system, or even convert everything into kilometer per hour or anything kilometer according to your convenience. So now, suppose we just learn this conversion. Suppose it's 36 meter per second and there's 36 kilometer per hour. How to convert this into meter per second? Now it's very easy. Just write it like this: 36 into kilometer by hour. Now, 1 kilometer equal to 1000 meter, and we got our SI unit here, and 1 hour equal to 60 minutes, and 1 minute equal to 60 seconds. So 60 minutes equal to 60 into 60, that is 3600 seconds. So 1 hour equal to 3600 seconds. We'll just put it here, that is 1000 meter by 3600 second. Just cut it. 5 2s are 10, sorry, 2 5s are 10, and 2 18s are 36. 18 2s are 36. So it will become 10 meter per second. Similarly, if you have to do the reverse, that is, suppose it's 36 meter per second, you can just write it as 36 into meter per second. 1 meter equal to 1 by 1000 kilometer. 1 second is 1 by 3600 second, 3600 hour, right? It's the same thing. If 1 hour equal to 3600 seconds, then 1 second equal to 1 by 3600 hour. This is the unitary method. So 36 into 3600 by 1000. We'll just solve this and find out some answer. Okay, in this calculation. And there's another trick. I just rub this to make space. That is, when you're converting from kilometer per hour to meter per second, you're just multiplying it with 1000 by 3600. And when you cut them, this is 5 by 18. This comes as 5 by 18 always. You can see it here. It's when you cut the 1000 by 3600, it comes 5 by 18. So if you just remember this number, 5 by 18, you can suppose it's 72 kilometer per hour. And you want to convert into meter per second. So just multiply directly 5 by 18, and it's just 4 equal to 20 meter per second. And you can also do the reverse, that is, suppose it's 20 meter per second. So from kilometer per hour, meter per second, you multiply it by 5 by 18, and from here to here, you divide it by 5 by 18, or you multiply it by 18 by 5. You just reverse it. Did not divide, you just reverse it into 18 by 5, that is 4, equal to 72 meter per second. Just remember this number, 5 by 18. Okay, I'll write it in different pen. I'll just write this thing clearly here. That kilometer per hour converting to meter per second into 5 by 18, and this is into 18 by 5. You're just reversing this, right? So this is remembered. This is the shortcut. So we move to our next topic. We'll discuss acceleration. So what is acceleration? Acceleration in mathematical form is basically the change in velocity in a specific time. Okay, by time. So suppose we assume v is the final velocity, u is the initial velocity. You'll find this representation in maximum books. Okay, like v is the final velocity and u is the initial velocity. And t is the time to go from u to v. Okay, so acceleration equal to v minus u by t. This is acceleration. And this acceleration is a quantity that controls speed. Now, how does it do this? Let's suppose this is a block moving with velocity v in this direction. Now, suppose the acceleration also acts in this direction. So, velocity and acceleration are in same direction. This means the acceleration supports velocity. So, the velocity will increase as a result. And in the opposite case, suppose if a body is moving at velocity v in this direction and the acceleration is acting backwards, that is opposite to velocity. So a and b are opposite. It will just, so basically a resists velocity. which makes the velocity become less, which decreases the velocity. So this is acceleration. Let's move to the next topic. Very simple topic. So basically, uniform motion is when the acceleration is zero. When the acceleration is zero, just know this, you'll understand this, I mean, completely understand this later. You just know this by now that in uniform motion, the acceleration is zero. And when acceleration is zero, obviously, because there's no one to support or resist the velocity of a body is same. We can also write that the velocity is constant. It does not change. So in uniform motion, the acceleration is zero, and because of that, the velocity is constant. And when the velocity is constant, we call it uniform motion. Now we'll get into the actual maths part of and the calculus part of motion in one dimension, and this will carry for the entire physics. Suppose there's a man who's running towards, suppose this is a cake. Okay, this is a cake, and this man is running towards the cake. So when he's running, he's moving with suppose 10 meter per second. And the cake is here, it's far away from him. So obviously his velocity will decrease with time. Suppose now it's 7 meter per second. Suppose it's 5 meter per second. When it reaches the cake, it will have, just before stopping to eat the cake, it will have its velocity 2 meter per second. Now these are specific instants where the man has different velocities. In here, the man has 10 meter velocity. So the instantaneous velocity at this point is 10 meter per second. Instantaneous velocity at this point is 7 meter per second. Instantaneous velocity in here is 5, and here it's 2 meter per second. So basically at each instant there's a different velocity. It may not be different, but in this case it's different. And this is a term we call instantaneous velocity. Okay. So if we see this is the point A, this is the point B, and this is a position. Okay, this is of distance x. And if we take a very small element called dx, like infinitesimally small, and what is infinitesimally small? That almost is equal to zero. Okay, it's infinitely small. Suppose there's an element dx, and there's a lot of dx in here. Okay, the whole line is made up of a lot of dx, infinite dx. And when you integrate the dx, all the dx's, you get x, which is the total distance. So suppose I'll just take only one dx here for convenience. So suppose this is dx and it's covered in time dt. That is also very infinitesimally small time. That's almost equal to zero. So, and why do we take this as infinitesimally small? To find the exact moment of the, like, what speed is in that exact moment. So we write this as like velocity equal to distance by time, right? So for an instantaneous velocity at a very minute instant, we write it as dx by dt. And also we can say this as, if we differentiate instantaneous velocity, if we differentiate position, that is x, with respect to time, write it here, differentiation of x position with respect to time gives us instantaneous velocity. Okay. Or speed, this is interchangeable. And I told you that when we get into the mathematical aspects of solving problems, speed and velocity are almost same. So we use them simultaneously. So now, suppose, and like in here, if you know that the object is going from A to B, you know the direction is this way, right? So the instantaneous velocity is also in this direction. For a particle which is not moving in a straight line, that is, suppose a particle is here and then it's here, it's moving like this, it's moving like this, moving like this, Now it's here. So basically, it is a curved path. Now, how do we find the instantaneous velocity at each point? Like this at, let's take a different pen. So at this point, the velocity is in this direction. At this point, the velocity is in this direction. It's in this direction, and this direction in each point. So at each point, the direction of velocity is changing. Now, how do we determine that at each point, what is the direction of velocity? So we can do this by, suppose this is a curved path, and you want to find the direction of velocity here. So you will just draw a slope or a tangent here and see, suppose it's going from A to B, you know that. So the instantaneous velocity is in this direction. Okay, equal to dx by dt. Suppose the body is going from B to A, okay, in this direction. So we just draw the slope and the instantaneous velocity is in this direction, right? So this is how you find the direction of instantaneous speed and velocity. Now we come to acceleration. Acceleration is like the same as what position was for velocity. Acceleration is the differentiation of velocity with respect to time. What is dv? dv is the change in velocity. And what is dt? That is change in time. Okay. So, and basically here also dx was change in position only. Suppose this was x1 and this was x2. These are very small, and like when you subtract them, that is equal to dx, it comes almost zero. That's why we write it as dx. Okay. So here also the change in velocity is dv, a very infinitesimally small change, and same as dt, very infinitesimally small. So we know that acceleration is change in velocity by change in time. So the same thing goes here, but it's just dv by dt to find the instantaneous acceleration, the acceleration at each instant. And it's another important thing is that this is one formula, and the other is a instantaneous, it's v dv by dx. So this is when we differentiate with respect to position. I'll just explain it to you like in a more ordered way, that when the velocity is a function of time, then A instantaneous will be dv by dt. Okay, because it's function of time, then dt will be used. When B is a function of distance or position, then A instantaneous will be v dv by dx. Okay. And I'll just give you a few examples after I just tell you this, and uh, everything will be clear. Just one second. Suppose we take this color. I'm sorry. Suppose for constant quantities, what is constant? Which does not change. Which does not change. And what is constant? Suppose velocity is same. Velocity is constant. That is like in uniform motion. Now we know what uniform motion is. That is when acceleration is zero, that makes the velocity constant, right? So in a mathematical form, we can say this. Suppose when the velocity is constant, so dv, what is dv? That is difference in velocity. Like you used in like when we're studying acceleration, we told acceleration is just v minus u by t. Now in here, the v is same, right? So v equal to u. The acceleration in any point is same. The acceleration is constant. So the initial and final velocity will be same. So the difference between them will be zero. So dv will be zero. So acceleration instantaneous will be dv by dt, that is 0 by dt, that is 0. So in here we proved that when v is constant, the instantaneous, just one second. The instantaneous acceleration equal to 0. This is how we proved it backwards. We saw the practical knowledge that acceleration increases or decreases velocity, and when acceleration is not present, the velocity is constant. Here we saw when the velocity is constant, if we differentiate velocity, the difference in velocity comes 0. So the acceleration instantaneous value is 0. Okay, so this is how we crossed it. And now I'll just give you an example. Everything will be cleared by this. Suppose, and the same thing goes for like position, etc. If position is constant, then dx equal to 0. If dx 0, then v instantaneous equal to 0. Okay, same thing goes for v. So I'll just give you an example. Suppose there's a position x with 4t square plus 5, right? So we can tell that find the velocity instantaneous. Obviously, I'll not write instantaneous every time, just assume it's instantaneous. V and A at t equal to 2 seconds. So when t equal to 2, at this instant, when time equal to 2 seconds, find the velocity and acceleration. So what is this? X is a function of time. This is t. This is a variable thing, right? And x is not constant. Why? Because according to t, the value of x changes. Suppose t equal to 1. So put t equal to 1 here. So it's 4 into 1 square plus 5 equal to 9. If t equal to 2 here, then x equal to 4 into 4 plus 5, that is 16 plus 5 into 21. So I hope you get the point that x is variable, the position is variable, it's not constant. So to find v, what was v? Differentiate x with respect to time. So this is 4t squared dot, we'll just take them common. I hope you know basic differentiation. So 5 is a constant, obviously, so the differentiation will be 0. So the answer is 8t. Now we have to put t equal to 2 here, as that is the instant we are talking about. So 8 into 2 equal to 16 meter per second. This is the velocity, the instantaneous velocity at 2 seconds. And this is not over yet. Now the velocity came as 8t, right? How to find the acceleration now? Now, if acceleration is differentiation of velocity with respect to time, so we'll do that, and the answer is 8. Now, 8 is a constant. 8 does not have any variable with it. 8 is just 8 meter per second. It's just constant, right? 8 is 8. So there's no way to put like 2 meter per second or like time 2 seconds in here. So we know for the entire journey, the acceleration is 8. So suppose I'll erase this to give you another example. So suppose it's x equal to, or yeah, or I just write it v equal to 2t to the power 5 or 2x to the power 5 plus 6x. Okay. Now what is acceleration at 2 seconds? Sorry, at x equal to 2 meter. So when the body reaches x equal to 2 meter, what is the instantaneous acceleration? So we know acceleration is v into dv by dx. That is v multiplied by the differentiation of velocity with respect to x. Now why is that? Because the v is variable with x here. The x is variable here. V is a function of distance. We have talked about when v is a function of distance, that is this one, right? This one. So we'll just find out dv by dx. That is equal to 10x to the power 4 plus 6. Now this is dv by dx. And to find the acceleration, we can just write v dv by dx. That is v is 2x to the power 5 plus 6x multiplied by 10x to the power 4 plus 6. Now you will just calculate it and put x equal to 0, sorry, x equal to 2 meters here and find the answer. Calculation will be a lot longer. I'll just not go into that. So this is how to find the acceleration when the velocity is a function of distance. And you can combine this by, I'll tell you about the graph functions that when it's x square, y z coming, when it's t square, why the acceleration coming as constant. When it's t cube, why isn't the acceleration coming as constant? We'll learn it from the graph knowledge. So suppose the acceleration, sorry, the position is c t cube plus 4t. Find at t equal to 1 second. Find everything like the acceleration, velocity. So velocity is obviously dx by dt. So it's 9 t to the power t square and it's 4. So 9 into 1 plus 4 equal to 13 meter per second. And acceleration now. So v equal to 9 t square plus 4. 9 t square plus 4. Now v is a function of time obviously. So acceleration will be dv by dt. That will be 18 t plus 0. This 4 is a constant equal to, and just put t equal to 1 here. So the acceleration here is variable, and when we put t equal to 1 here, it comes as 18 meter per second square. This is the instantaneous acceleration. I hope you have understood this. Let's move to the next topic. So now we have studied the differential equations of like velocity, acceleration, position. We can clearly establish a cyclic relationship between them. So that is, suppose this is x, this is v, this is a. To go from x to v, to go from velocity to acceleration, to come back from acceleration to velocity, come back from velocity to position. Now, if we differentiate x with respect to time, velocity is found, right? If we differentiate velocity with respect to time, acceleration is made. Or if we just use this formula, that is differentiation of x if the velocity is a function of distance, then if we use this formula, this one, then acceleration is found. Now, this is differentiation. Now, the opposite of differentiation is integration. So if we just rearrange this and somehow, like A is dv by dt, right? So dv equal to A dot dt. If we integrate them, this comes as v equal to integration of A dot dt. So separate thing. Now, if we want to go from A to V, we have to integrate A with respect to dt, A with respect to time. And similarly, if you want to go from velocity to position, you have to integrate the velocity with respect to time. You can also find it easily. How? That is v equal to dv by dx dt, and v equal to, I'm sorry, I just got confused myself. V equal to dx by dt. Now just take the dt here. So v dot dt equal to dx, integrate them. And you'll find that x equal to integration of v dot dt, which we have written over here. So this is the same thing. If you differentiate one thing, it becomes x differentiate with respect to t, velocity. If you differentiate velocity with respect to time, acceleration, or use that other formula in case of function of distance. Integrate acceleration with respect to time, forms velocity. Integrate velocity with respect to time, forms position or distance. So this is the cyclic relationship. We move to our next topic. So now we'll move to equations of motion, and there are 3 equations of motion. That is, and first we'll define some terms first of all. that is v, is final velocity, u is initial velocity, t is time obviously, a is acceleration, and s is displacement. It doesn't always have to be x. It may be x, you can take it as x, but I'll just take it as s, as in most of the books, it is given as s during solving the equations of motion. So the first equation of motion is v equal to u plus or minus at. This is one. Second one is s equal to ut plus minus half at square. This is the second one. And the third one is t square equal to u square plus minus 2as. Now, there's one very important condition that applies to all three, that the equations of motion are only valid when the acceleration is constant. For variable acceleration, these equations of motion won't work. This is very important. Okay, and why is that? Because here the value of a, it's singular. You can put a single value of a. You have to put a value of a here, right? So if you put some 80 and it is like 80, suppose suppose acceleration is 80, like in the last example. So v equal to u plus minus 8t into t, that is u plus minus 8t square. So the dimensions don't really match. You see, this is, you haven't read unit and dimensions probably, but this is like a law of homogeneity, that this u, the unit is meter per second, and this is time square, that is s square. You can't just add meter per second and some time square. First of all, there's nothing called time square. That's not a real quantity. But you can't just add random units together. It's like adding 1 kg mass to like 2 meter per second velocity. It does not make sense. So the whole dimension changes. Okay, so the whole dimension changes and the problem just becomes illogical. So only an variable acceleration is there, 100% it's there, but you have to solve it in a different way, which is completely out of the curriculum. It's like they're way harder numericals, which you don't really need to practice. So this only works in constant acceleration. Now, when will you use this thing? There are three formulas, right? So when will you use each of them? Suppose v is given, u is given, t is given. You have to find out a. Now in equation, we have to analyze and see that this equation has all three. V is there, u is there, t is there. So you can easily find out a by solving the equation. Suppose there is u present, t present, a you have to find, and a present. So find the displacement. You can easily say displacement equal to ut plus minus half e t square. Okay. Or you have to find the a where velocity is given, initial velocity and final velocity are given, and the displacement is given. So just v square u square plus minus 2as. You can just put the values of a, u, and b to find the value of s. Now, why I'm saying plus minus? It's because the value can be v equal to u plus at or v equal to u minus at. According to our sign convention, the directions we take as positive and the directions we take as negative. That's why we talked about sign conventions, and these are extremely effective in problems, including the equations of motion. So I'm writing plus minus because it can be both plus or minus according to the question. So suppose I'll just take an example. A body moving with velocity 5 meter per second and accelerate with 10 meter per second for 2 seconds. Find the final velocity. Now, solving physics questions, it really helps if you just write what's already given and what you are required to find. So, the body is already moving with velocity 5 meter per second. So, the initial velocity equal to 5 meter per second is given and accelerates with 10 meter per second for 2 seconds. So, the acceleration is given 10 meter per second square. I'm sorry, 10 meter per second square. The time is given 2 seconds and final velocity is asked. So, just put the formula like this. And it is told accelerates. Okay. So V equal to U plus AP. And by accelerates, I will give you the context why I'm saying accelerates here with the next question. So V equal to 5 plus 10 into 2. Just put U equal to 5 here, A equal to 10 here, and T here. So it comes as V equal to 5 plus 20. That is the final velocity is 25 meter per second. Suppose the acceleration, I'll just write it in statement by when acceleration acts opposite to velocity, it causes deceleration and is called retardation. So acceleration is velocity increases. When acceleration happens, the velocity increases. When retardation happens, the velocity decreases. You can also call it negative acceleration. And also very important thing. Suppose in a lot of sums, the time of the answer may come negative. So it does not make the answer not possible or wrong. Okay. The thing is, when the answer comes negative, then that implies that the direction you had already like picked as positive, or like the velocity you had already picked, which would be going suppose in the positive direction, it is in reality moving in the negative direction. It is moving in the opposite direction. So suppose in the answer 5 meter per second is the answer, and you have assumed that the body is moving in this direction with 5 meter per second, but the answer is minus 5 meter per second, right? So it will move in this direction in reality. You have assumed this earlier, but in reality, it would be this. Okay, the minus implies the direction you have already taken. It's just the opposite direction that's happening in reality. Okay, it may seem confusing right now. If we take some examples, you'll find it more clear. So we just take this example to end the conclusion about science, and also this has some other things in it that we just discussed this. A car is moving with 36 kilometer per hour and it has retardation 2 meter per second square. So find the time required for the car to come to rest. So the first rule about solving physics questions is just write down what is given and what you have to find out. So a car is moving 36 kilometer per hour. U equal to 36 kilometer per hour. Okay. It has retardation 2 meter per second. Now, retardation is what? It's negative acceleration. It's minus 2 meter per second square. Okay. And find the time required. So, time is unknown for the car to come to rest. And what is rest? Rest means the final velocity is 0. The car comes to rest. Okay, so the velocity, the car is not moving, hence the velocity is 0. The final velocity. So, and there's another thing, that is, if you look close, the unit, this is in kilometer per hour, this is in meter per second square. You can't just use it like this only. You have to convert the units to one. I prefer to convert them into SI units, that is meter and second. Convert this 36 kilometer per hour into meter per second, and how are you going to do that? That is 36 into 5 by 18 is to, that is 10 meter per second. So, and also U is given, A is given, T is given, T is not given, V is given. So you can use this formula, V equal to U plus AT. Now, put the value of V, that is 0. Initial velocity was 10 meter per second after converting. So don't put value, don't put the units here. 10 meter per second plus the A is minus 2 into T. Because it is retardation, we're taking the minus sign here. Okay. So it's minus 10 equal to minus 2t. So the negative sign gets cut. So time equal to 5 seconds. So the car takes 5 seconds to stop. So this is the confusion about the sign. Whenever I just like to take it like this, that whenever there is deceleration or negative acceleration or retardation is told, just use minus 2 meter per second or like minus in front of the acceleration. You don't have to do like use V equal to U plus AT and then just assume the acceleration positive. Then and that becomes a mess. Many people do that and the sign becomes the opposite. The sign comes the opposite. You have to again convert the sign. Just don't. If retardation is told, the main crux is just assume a minus in front of the acceleration. That's it. When this question is told that the car is moving with velocity 4 meter per second for 5 seconds to cover a distance of 100 meter, find the acceleration. So U is given 5 meter per second, T is given 5 seconds, sorry 4 meter per second, and S is given 100 meters, that is displacement is given. So acceleration has to be found out. So if you check the equations, this fits the best. Why? Because S is given, U is given, T is given, here also T is given, acceleration you have to find out. So just put the values here, A equal to UT, that is 4 into 5 plus half into A into 5 square. 100 equal to 20 plus half is 25. 80 equal to 25 by 2. A by 5 is 25, 16. So it's 32 by 5. A. This is the answer. Okay. A equal to 32 by 5 meter per second. You can convert it into like decimal, that it's 6.4 meter per second. So ball travels with 3 meter per second, and when it completes a distance of 4 meter, it reaches a velocity 5 meter per second. Find E. Now, what's given is U is given, that is 3 meter per second. V is given, that is 5 meter per second. S is given that is 4 meters. Now A is unknown. So the formula most fitted for this is V equal to U square plus 2AS. Why? Because V is given, U is given, S is given. You have just have to find A. So just put the values here. Is 5 square into 3 square plus 2A into 4. That's 25 equal to 9 plus 2A or 8A plus 16 equal to 8A. A equal to 2. This is our answer. A equal to 2 meter per second square. Now stopping distance. Suppose there's a car. This is a very ugly car. And it's moving with a velocity u, and it suddenly applies brakes. Now, when you apply brake, the car moves somewhat forward and then it just completely stops. So, and if you're traveling at a like very, very high speed, so the car before stopping, when you apply the brakes, it will just move some distance and then stop. So suppose it moves with you, you apply brakes here, and the car here comes to rest. That is the velocity zero. The final velocity is zero. Now, before coming to rest and after applying brakes, the distance traveled is called the stopping distance. So stopping distance is distance traveled till the velocity of body becomes zero. Okay, or the velocity on the body comes at rest. Now, it doesn't always have to be a car applying brakes. It can be a particle that is moving with a velocity u and stops after traveling a distance s. Taking the example of a car and using brakes is more practical because a car moves, it applies brakes, and it travels some distance and it stops. So it's easier to explain. So, what is the formula of stopping distance? We just take this equation 2as, or rather minus 2as. Why? Because to stop the car, the velocity has to decrease, right? The velocity u was there. Now this u has to decrease and finally become zero. That is v. Now what brings this decrease in velocity? That is retardation. We've already talked about how acceleration controls the velocity. It increases or decreases the velocity. So when negative acceleration or retardation is there, the velocity decreases. So we use this v square equal to u square minus 2as. So we use this as like plus minus a into s. We have taken retardation here. So the final velocity is zero, obviously. Initial velocity is u square minus 2as. So u square equal to minus 2as, s equal to u square by 2a. This is the formula of stopping distance. Suppose I'll just take an example. I'll not write the whole statement, but just know this, that suppose a body is traveling with velocity 4 meter per second, or yeah, 4 meter per second, and the acceleration or the deceleration, the retardation of the body is 2 meter per second. Find stopping distance. So you can use this as, first of all, there's this method. You can directly use the formula, that is s equal to 4 into 4, that is u square, by 2 into a. So this will give you, this will be 4 meters. And there's another, the formula based one, that is v square equal to u square plus 2as. That is, you put 0 here, you put 4 square here, plus 2 into or minus 2 into 2 into s. As 2 meter per second is retardation, so it's basically minus 2 meter per second. So it's minus 4 square minus 2 into 2s, that is, the minuses get cut, 16 into 4s, that makes s equal to 4 meters. Both the answers are same, just found out with different approaches. This one is the direct formula approach, and this is the like equation wise approach. There's another thing to mention, that is displacement in the nth second, that is SNF. Now what is this? Suppose we have already talked about how to find displacement, velocity, this and that in time equal to, suppose, 1 second, 2 second, 3 second, 4 second, and so on. Okay, if there's complete second, but what if you have to find the displacement when t equal to like the second or the fifth second? This is completely different. Fifth second is not equal to 5 seconds. Okay, so what does fifth second mean? Fifth second is the interval between 4, 4 seconds and 5 seconds. It's the time interval between. It's the time interval between them. So it's a completely different, and there's a formula for it, that is S equal to U plus minus A by 2n minus 1. So this is the formula where n equal to the nth second. Suppose nth second. Suppose if it's fifth second, just put 5 in here in place of n and just do it in form of any other equation of motions that we have already practiced. Like find the displacement of body in 6 seconds if it starts from rest. Rest with acceleration 16 meter per second square. Now just put the values here. S nth, the formula is this, displacement of a body in 6 seconds. So this you'll just know that when 6 seconds is given, this is the formula for nth. So starts with rest, that is u equal to 0, initial velocity equal to 0. So 0 plus 16 by 2, 2 into 5 minus 1. So 8 into, this is 10 minus 1, 9. This is 72 meters. This is the distance traveled. The next topic is motion under gravity. Now, first of all, what is gravity? Gravity is basically nothing but acceleration. What is gravitation force? The force that pulls you towards the center of the earth. That is gravitation force. And what is gravity? That is just acceleration. So we define it by g, and its value is, like, the accurate value is around 9.8 meter per second, or we take it as approximately 10 for calculation purposes. Now I'll explain this in a minute. First, we have to understand what a ground-to-ground projectile is. Suppose this is the ground and a ball is thrown vertically upwards with velocity u. So what happens is the ball goes up, stops at this point, stops at the highest point, and again comes down with the same velocity. Now this is the rule about which this statement is, that in absence of external resistance, the velocity with which the ball is thrown up is the same velocity as the ball had just before touching the ground. Basically, when it touches the ground, then the velocity changes because of other factors called elastic factors, and that's a different issue. But just before touching the ground, the velocity with which it was launched is the same as the velocity that it comes down. The same velocity that the velocity that it goes up, same as the velocity with which it comes down. And in the meantime, at the highest point, what happens is this particle comes at rest. Now, how does this happen? First of all, suppose this velocity is going upwards and g always acts downwards. So suppose in this part, I just divide it. In this part, that is 1, and this part, this is 2. So in 1, basically what's happening is u is in this direction and g is in this direction, that is opposite. So what happens is the ball moves up and the velocity continuously decreases, because we have talked about earlier that the acceleration controls velocity, and when they're opposite, when they are completely in opposite in direction, when the velocity decreases. So the velocity decreases at a point which is the height, maximum height of the projectile. It completely becomes 0. Now, in part 2, it just becomes the opposite because u is acting in this direction. Suppose in here, this is at rest. Now it falls down like this till it attains u. Now, the velocity here is in this direction, right? So the velocity is in downward direction and g also is in downward direction. So they are in same direction. So they'll support and the velocity will increase. So from 0 here, the velocity will increase, increase, increase and reach the velocity with value u just before hitting the ground. So this is how a projectile basically happens. And there are a lot of terms we can define with this projectile. That is, suppose the maximum height reached by the projectile, the time of flight, the total time required when the ball is launched up and the ball comes down. That is the time of flight. We can hear some things like this. So mathematically, h max is the highest distance from the ground reached by the particle. A particle during a projectile. We'll understand a lot about projectile in the next chapter. The next chapter is completely entirely about projectile. So what is projectile, this and that? Basically, you project a ball and that is projectile. Okay, you project a ball upwards. And there are many variations to the projectile. You'll understand in the next chapter. So the highest distance from the ground reached by a particle during a projectile is the h max. This is the h max, where the velocity becomes 0. Okay. So you can just put it with, suppose, this side of the projectile. You can take this one as reference and see that you can just put it in the equation of motion. Okay, now look. In here, the u is in this direction and g is always downwards. So take this as negative. You can also take the opposite, but just prefer this. Okay. So v square equal to 0 as it becomes 0 at the top, equal to u square, and 0 at the top when it reaches h max. So u square is u square plus 2 minus g s, or I'll just write it as h max. This is the displacement, right? From here to here, the displacement is h max. So u square equal to 2g h max. So h max comes around as u square by 2g. So basically this is like stopping distance, and stopping distance was u square by 2a. Instead of a, here's just g because the a is given here. Okay, so this was the h max, and the next is time of flight. TOF, time of flight. That is the ball launching here and coming down. The time required for this whole motion is the time of flight. Now, how to find this? Suppose then the initial velocity here is u. Okay, initial, or I'll just write vi, and v final here it is minus u because the direction is in this direction. That we assume negative. Also, g is negative because it is in this direction. So the acceleration is minus g. If you put it like this, v equal v final equal to v initial plus at, and we define and we represent time of flight with t. So it's minus u equal to u plus minus g into t. So t equal to, or rather gt equal to minus gt equal to minus 2u. So t equal to 2u by g. This is the time of flight. If you see it in other ways, that this is the whole projectile, right? Now what will be the time required to reach the h max? That is this. If the whole thing takes For the entire projectile to go up and come down, for just going up, it will just take half the time. Okay. So to go from, suppose this is 1.1, 0.2, 0.3. So 1 to 3, it takes 2u by g time of flight. Okay. But to go from just 1 to 2, it is just half the distance traveled. So it will also take half the time. And why is this applicable? Because the acceleration is constant. So this will be t by 2, that is u by g. Suppose I'll give you an example. A ball is thrown up with 10 meter per second velocity and with 10 meter per second velocity, and find the h max and time of flight. Assume this will be given in the question, that assume g equal to 10 meter per second square. Many questions it may be given that g equal to 9.8. So you have to assume 9.8 there. So a ball is thrown up with 10 meter per second square, 10 meter per second velocity. So the h max, that is this distance, will be simply u square by 2g, equal to 10 into 10 by 2 into 10. So the maximum height is 5 meters from the ground. Now what will be the time of flight? Time of flight will be basically 2u by g, that is 2 into u is 10, g is also 10. This will be 2 seconds. Okay, it's very simple. And also if it told that what will be the time required to go from the initial point to the maximum height, to h max. So initial point to h max. What will be this? This will be u by g. As this is literally half the distance, this will take half the time to travel the entire path. So this is 2u by g by 2, 2 by cancels out. So that will be u by g, that is 10 by 10 equal to 1 second. And this is exactly the half of this. This is the time of flight, and this is to reach the maximum height. In context of motion under gravity, suppose there's a tower with a man standing on top, and he has a ball in hand, and he just drops the. So what will be the time required for the ball to come to the ground? Now, there's also a very easy concept, that this ball is here right now. This ball will fall down on the ground here. Now, if we assume this direction, upward direction, as positive, as we have always assumed, so the g will be acting in this direction, so it will be negative. We have done this, right? But the ball, it's traveling h displacement, right? But in this direction, that is minus h. The displacement will also be negative, because it's displacing it in this direction. If the ball was thrown up and it would have traveled in this direction, then the displacement would be positive h. But now is just negative h, because you've taken the downward direction as negative. So just one second, again, downward direction as negative, so the displacement is minus h. So you can take this as this. I'll just solve it like this. S equal to ut plus half at square. Why I'm using this? Because the displacement is given, that is h, or minus h rather. U is given, and as it is dropped, the initial velocity is 0. If it was thrown from the tower, it should have had some velocity, but since it's dropped, then the initial velocity is always 0. So this will be 0, and this will be half minus g t square. Okay, so h equal to minus half g t square minus sin square. Now t equal to root over 2h by g. the formula. Now second, if I try to assume this direction as negative, the upward direction as negative, and the downward direction as positive, what will happen? G will become positive, obviously, and the displacement will also be positive because it is displacing in the direction that we have assumed positive. So I just write it as H equal to ut plus half gt square. H equal to ut is 0 because the initial velocity is 0 in any way. So gt square t equal to 2h by g. Okay, so suppose a tower is 100-meter long and a man standing on top drop the ball, or I will assume it at 2000 meters tall, 2 kilometer. Okay, this is 2000 meters tall, and a man standing on top drops a ball. Find time to reach ground. So the answer is time to reach ground is nothing but 2h by g. So we'll assume g equal to 10 here. Okay, it's 2 into 2000 by 10. It's root over 400. That is 20 seconds. This is our answer. Now suppose in the last tower sum, suppose this is the same tower and the man is standing on top. He had not dropped the ball. Instead, he had thrown the ball upwards. So this is the same tower H. This is down. So what will be the motion of the ball? First of all, the ball will go up and it will come down like this. So basically, if we take it as like this point, so from here is the tower. Okay, so the ball goes up, reaches a maximum height, just like the ground to ground projectile, reaches a maximum height, the velocity becomes 0, and the velocity increases, and it reaches the ground. Now here, the u will not be u because the velocity will not be u because here the velocity was u. Since it has traveled an extra distance this, so it will gain some speed because the gravitation is also acting in this direction, right? So the speed will increase, the u will increase. This will be something called v. Okay, I'll just erase this. Now, you can also see one thing, that the initial point was this. Initial point was this. The final point is this. The difference between the initial final point is the displacement, that is h. That is this and this. Displacement is h. If we assume, for our convenience, like we saw in the previous question, that if we take the downer side, the lower side as positive, lower side of this line. Okay, this is the frame of reference for us. Below this, it's positive. Above this, it's negative. And we saw why, because the g and the h, the displacement, both becomes positive. So it's easier for us to calculate. Now, if we take this direction, the lower direction as positive, the velocity v or u with which the ball was launched, this becomes negative. Okay, because it's in this direction, the upward direction, which we have taken negative. So if we just write the equation, that is h equal to minus ut plus half gt square. If we had taken the downward direction negative and the upward direction positive, it would be minus h equal to ut minus half gt square. The displacement becomes negative and the g becomes negative. So the negative sign comes here. The same thing, but here we have a initial velocity, that is u. So we start with basic graph knowledge, and the first topic here is equation of a straight line. Now, as far as in my knowledge, First of all, I know that this has been taught to in the 9th grade. And for the people who weren't getting high, probably already know this. And the people who were getting high and partying, don't worry, I'll teach from the basics. So this line, this straight line coming in between the x and the y axis is represented by y equal to mx plus c, where y is the y coordinate, x is the x coordinate, m is the slope, and c is the y-intercept. So we'll start with what is the y-intercept. Suppose I'll just draw the same graph, or I'll write the definition firstly. Y-intercept is distance between origin of straight line rather, and origin of y-axis. Suppose the line starts from here, okay, and it is 3 units. So this is the origin of the line. This is the origin of the line, and this is the origin of the y-axis, right? So the distance between them is 3 units. So the y-intercept will be 3. Similarly, if the line starts from the origin, the distance between the origin of the line, that is this, and also the origin of the y-axis, that is still same, this would be the same, right? So the distance between them will be 0. So the y-intercept is 0 in cases starting from the origin. Now, what is slope? Slope is nothing but gradient. Okay. And it's basically represented by m, which is equal to tan theta. This is the most basic one, okay, tan theta. Now, gradient is anything like, as I showed you, suppose this is a line, straight line, and we are taking a point here, okay, and the coordinate of this point is x1 comma y1. So this is y1, this is x1, and this line is starting from the origin. Okay, so we'll take this as the gradient. What is equal to tan theta? What is tan theta? That is perpendicular by base. So the perpendicular is y1 minus 0 as the line starts from the origin by x1 minus 0 equal to y1 by x1. That's basically tan theta, or basically the gradient, if we consider the origin, that is 0 comma 0. Similarly, the slope of a straight line is always same. Slope of straight line always same, even if you take any point in the middle. Suppose you're finding out the slope between this point, suppose x1 comma y1, and this point x2 comma y2. So we'll just draw this, that m equal to tan theta equal to y1 comma y2 by x2 comma y1, y2 comma y1 by x2 comma minus x1. I'm not sure that I've said this right, but tan theta is basically, if you consider these 2 points, this point and this point, you just have to subtract these two. In the earlier case, we had taken this point and we had taken the origin. We had taken it from the origin. These are the 2 points that we have found out the gradient in between. So tan theta here is y2 minus y1 by x2 minus x1. Okay. Suppose I just give you a line. So what will be the equation of this line? So first of all, we'll write y as y, because y and x are constant. I mean, they don't change in this equation. So y equal to m m is the slope, that is tan theta, and here theta equal to 60 degree. So m equal to tan 60, m equal to root 3. The slope equal to root 3. So root 3x plus, because it is 5 units above the y-axis, above the origin rather, or origin of the y-axis, then it will be plus 5. The same thing was, this line is originating with 60 degree here, 5 units lower than the origin, then the equation would have been y equal to root 3x, because the slope is same, because the angle from the horizontal is still 60, minus 5, because it starts beneath the origin. Okay, so this is basically straight line knowledge. And also there's one more thing. Let's suppose there's a graph like this. This is called the constant graph. Okay, why? Because if you write the equation of this line, suppose this is c meter away from the y-axis and the origin. Okay, now this line is parallel with the x-axis. And what is the angle between two parallel lines? That is theta equal to 0. Two parallel lines have 0 degree in between them, right? Anti-parallel have 180 degree. Parallel have 0 degree. So basically the slope is m equal to tan 0. And tan 0 is basically sine 0 by cos 0, which is 0 by 1, which is 0. So m equal to 0. If you write the line mx plus c, so y equal to, as m is 0, this becomes 0 equal to c, which is constant. I'll give you one example to show you better. That suppose this is the position time graph. Okay, so the position here, which is represented by the y-axis, is same at every point. The time is increasing. Okay, the time is increasing in the x-axis. You can see that the x-axis is increasing. The graph is increasing in this direction, but it's constant in this direction. Okay, in the y-axis. So this indicates that the x is constant while t increases. This is the graph of rest. Why? Because the position is constant or doesn't change with time. If you remember that when we studied the first topic, that is rest and motion, the definition of rest was, rest is when the state of a body, when the body does not change its position with respect to time. So this is the graph of rest and, position and time, which depicts rest. Now when we see a graph like this, we usually also have a portion like this. The graph basically extends from here to here. It's not, we just draw this portion and we omit this portion. The thing is, the straight line is like this. Okay, in reality. Now, what happens? So this is suppose 60 degree. Okay. What happens? The line is like this, coming from the origin, but like this. This is the reverse. This means, and also this is 60 degree. Okay. This means that the slope is negative, because we considered this as positive. Okay. Or we can just draw a tangent like this. This is going upwards, right? Upwards means positive. This is just a trick. This means downwards, right? So this means negative. So the slope here is negative. So the equation of this line is y equal to mx plus c here. So y equal to root 3x plus 0, as it starts from, I just omit the 0 part. This is the equation of the line. And here the equation is y equal to mx plus c, y equal to minus root 3x plus 0, which is this minus root 3x. Okay. This is when the reverse happens. Now what will you do when curved paths happen? Suppose there's a parabolic graph, parabolic or hyperbolic, anything. Suppose like this. Now, to find out the slope here. First of all, these are represented by functions other than linear functions. These are not linear functions. I'll talk about the functions later. The thing is, we will be learning how to find the slope. So, to find the slope of a curved path, to find the velocity, what we used was tangent. We just drew a tangent to the line and drew that the velocity was in that direction. Okay. So here also, we will do the same. We just draw a tangent. Suppose we divide it into two and see that this is the tangent of this curve, and the theta here is acute, that is less than 90. And when this happens, the slope is positive. Okay, when you see this here, the slope makes theta more than 90 degree. This is 90 degree. So the slope makes, so the theta is more than 90 degree, which makes it obtuse. And for obtuse angles, the slope is negative. Okay, this is a rule of thumb. And also at the top, if you draw the tangent to the line, it becomes parallel to the x-axis. So at the very top, the slope is 0. We are finding now what is the link between the graphs we are finding, and we have studied till now, and 1D motion, because the graphs were graphs and 1D is 1D, right? So now we'll study the relationship between them. That is, suppose this is a graph, this is a straight line with theta, and suppose the y-axis represents the position x. This is not the x-axis, and the x-axis represents t, that is time. Now, when we find the slope of it, what do we write? Suppose at this point, it is tan theta. What is tan theta? Tan theta is, suppose this is x comma t. I'll just write it like this. Coordinates are x comma t, that is t by x. Sorry, x by t. So this is the perpendicular is x, and the horizontal is t. This is x by t. So if we take a very small element here, we can still write the slope as dx by dt, right? And what is dx by dt? That is nothing but velocity. So we know this, that, write it with a different pen. The slope of xt graph, that is position time graph, gives velocity. Okay. And if we see the reverse, that is, suppose the graph is velocity by time. Now, what we had studied was velocity equal to dx by dt, and if we just rearrange this, that will be integration v dot dt. Now, integration is nothing but v dot dt, that is velocity and the product of time, the product of velocity and time. Okay, so if we find the area under this is basically the integrated area of velocity and time, right? The area under the graph is velocity into time, right? Because the area of a triangle is half perpendicular into base, right? Of a right angle triangle. So the base here is t, the perpendicular here is v. So it's basically product of v and t. With half that is a constant, I'm not talking about that. It's basically the product of v and t. So position is the area of x vt graph. So this is another very important rule. One is this, another one is this. Okay, so you see the cyclic relationship, that is xt. So the slope of xt graph equal to dx by dt, which is velocity. And when we see vt graph, the area under the vt graph, that is this, is the displacement. Why? Because v dot t or v dot dt equal to x. Okay, we say that it's just dx integrated by v into dt. So basically this will also integrate, this will also integrate. We just take it as a product of v and t. Okay, for mathematical purposes obviously. Similarly, for a velocity time graph, suppose this is like this, the slope m equal to tan theta equal to dv by dt. What is dv by dt? That is nothing but acceleration. And also, what is acceleration? This, if we rearrange them, this is v equal to integration of a dot dt, which is nothing but area under a t graph. So if this is the at graph, theta, the area under this graph, which is the area of this right angle triangle, that is half into height, suppose a, base suppose c, a into t, describes the velocity. So now we'll talk about parabolic graphs. So suppose, and this is a parabolic graph, okay. And most of the questions will be just drawing this part. Like in linear equations, linear lines, we used to draw this part and not this part similarly. So for linear lines, that is straight lines, the equation was this, right? Suppose it starts from the origin, so y equal to mx. And as m is a constant, the slope can be anything, but it is constant for a straight line, right? So y is directly proportional to x. Both have power 1. Y is proportional to the power x to the power 1. This is what makes them linear. Okay, y is directly proportional to x. Now for parabolic graphs or hyperbolic graphs, it is not the case. The relationship here is, the mathematical relationship is y is directly proportional to x square. Or for hyperbolic graphs, x is proportional to y square. Okay, you can just, if you have to determine which graph is x, y proportional to x square and which graph is x proportional to y square, you can just remember this, that y is proportional to x square, right? So the graph like this sleeps on the y axis, and here x is proportional to y square, right? So the graph sleeps on the x axis. This is just a simple trick. So now, how to find the slope of a parabolic graph? We have discussed about this earlier. Then just draw a tangent here. See that the theta, it is obtuse, so the slope will be negative here. Here, draw a tangent. See the theta. Theta is acute, so the slope will be positive here. And here, at this point, the slope is having angle 0 with, the tangent is having angle 0 with the horizontal at this point. So the slope is 0, m equal to 0, right? So now we'll get into how these affect the 1D motion, suppose this graph, this is an xt graph. Okay, and this is parabolic. Suppose the m slope is equal to 2. So the equation of line will be x is proportional to t square, first of all, because it is parabolic. And also the slope is 2. So the line will have the equation x equal to 2t square. Also, it's starting from the origin. That is like this. X is equal to 2 square. If it was not starting from the origin, suppose it was starting from here, this will also have a y-intercept. So it will be x equal to 2t square, that is slope in 2t square, mt square, plus suppose this is just the same thing. So this is x equal to 2t square plus c. It's just the same thing, exact same thing, like in the straight lines. So now, suppose this xt graph is like this, and the equation is x equal to 2t square. Now, the slope of this line is the tangent, right? And the tangent is m equal to tan theta equal to dx by dt. We did write dy by dx in the previous graphs. Similarly, this is the y-axis, this is the x-axis. So this will be dx by dt, right? What is dx by dt? As we've already talked about, it is v. So dx by dt equal to v equal to 4t. When you differentiate this, fine, this is 4t. Now here you can see that the velocity is directly proportional to time. Okay, so the graph between velocity and time will be a straight line because velocity and time are proportionate to each other linearly with suppose theta, but the slope here is 4. So the tan theta equal to 4, right? And similarly, it is 40, right? If we see the slope of this graph, that is dv by dt, slope was dy by dx, it's v on the y-axis, it's t on the x-axis, so it will be dv by dt, which gives this acceleration equal to the differentiation of this, which gives acceleration equal to 4. Now this is a constant, and we have already seen how constant graphs are drawn. That is like this. A is constant with the value 4. The time is increasing, but the acceleration is constant. Okay. So you can play with them quite clearly. Like I don't have space here, I'll just. Suppose this is a parabola with x proportional to t square. When you take the slope, it is dx by dt. So the t square, when you differentiate it, equal to v. So the v is always proportional to t. So it is linear. And if v is proportional to t, then dv by dt, when you is proportional, that is equal to a, is proportional to nothing. It is constant. Okay. So a is constant. If someone tells you that the a is constant, now find the graph of the position, you can seriously go and just mark this as the option. You have to just backtrack it. Now, similarly, if the same thing was negative, that is, suppose the, the parabola was like this, an inverted parabola, then it will be proportional to x equal to minus t, or I'm sorry, x equal proportional to t square, but slope is negative. Okay, it will be x equal to minus t square. Differentiate it, b equal to minus 4t. So it is minus 4t. It is the line this. Okay, this is v, This is t. I'll draw it first. This will be the line of v proportional to t with the slope m equal to -4. Why? Because if it was v equal to 4t, the line would be like this, and if you extend it, it would be like this. Now, since it's the reverse, since it has negative in front of it, it will just be the reverse. It will just be like this. So, and again, if you differentiate the same thing, v equal to -4t, so dv by dt equal to -4. That means equal to acceleration. The acceleration is -4. This is below the origin. The value of acceleration is -4 meters per second. Meter per second square. Okay. So this is the basic knowledge of the graph. We'll move to some specific one direction graphs. So we'll move to our next topic. So now we'll talk about position time graphs. So the first graph is this. We have seen this earlier, that when the position is constant and the time is increasing, the body is in rest. So this is the graph of rest. Now the second one. Now this graph is told constant speed or constant velocity. We use them interchangeably in maths. So how is that? Because this is the linear graph. This is straight line. So x is directly proportional to t. So if we differentiate x with respect to time equal to v, it will give us constant. Suppose the slope is, just assume something to make it easier. Okay. Suppose the slope is 4. Okay. So it is x equal to 4t. Right. So dx by dt equal to velocity equal to 4, which is a constant. So when the straight line is there, the velocity will be constant. And similarly in this graph, angle is obtuse, so the slope is negative. Suppose, again, you can assume anything to make it convenient. Suppose we'll take the same. So x equal to -4t. Okay, this is the graph. It obviously has a distance from here, but that's a separate thing. So the velocity, that is dx by dt, equal to -4. So the velocity graphs for the first one is like this, constant, and the velocity graph for the last one was like this. Okay. Similarly, which has been told that this is constant speed, this is constant velocity or speed in. Now for this graph, we've already seen this. This graph is also a parabola. Okay, this is an xt graph. What do you mean by parabola? X is proportional to t square. You can write it as this, or you can just mention it like this. They're all parabolas. Okay. So parabolas mean they are proportional to the square of the x-axis, right? So x is proportional to t square. Now we've already discussed this, dx by dt, and we'll assume a slope. Suppose x equal to 4t square. So dx by dt equal to v equal to 8t. You just use differentiation to determine the graph of the next equation that you like, next value that you like. Suppose I have x equal to 4t square. I'll just differentiate x to find velocity, to find the relation of velocity and time. So this is velocity, this is time, this is theta, slope equal to 8 here. And when you do this, this is velocity is proportional to time, and that is v equal to 8t. Now differentiate v with respect to time, you get a, that is constant, 8. Okay, so when you see a parabolic graph, one second, when you see a parabolic graph of position and time, know that the acceleration will be constant. Similarly, this is constant retardation or negative acceleration. This is parabola, negative parabola, which means x equal to suppose minus 4t square. Then v will be equal to differentiation of x with respect to time. It will give us v equal to minus 8t. So the slope is minus 8. So the graph will be like this. Like this. And if we differentiate this with respect to time, it will be minus 8. Okay, the acceleration will be constant, but it is retardation. It is retardation. So there's a trick when you can see that this graph results in positive acceleration, right? The xt graph, when the hyperbola is like this, it gives positive acceleration. And when hyperbola is like this, it gives negative acceleration. So you can just see a pattern here, that is, you just look at this. This is a smiley, okay? So smiley is positive. So the acceleration is positive, and here it is a sad face. So this is negative. So the acceleration will also come negative. Acceleration versus time graph. So this is a shortcut you can use. It's a very useful shortcut for speed or velocity time graphs. So we'll take the first one, that is velocity time. This is constant velocity, right? And what it has been told that this is the displacement, which is the area under the graph of the VT curve. On VT graph, it gives the displacement. Why? Because dx by dt equal to v, dx equal to v dot dt, that is v multiplied by t. So the displacement is given by this, which is the area under VT graph. We've explained this earlier, so I'll not elaborate. We'll move to the second one. That is, I'll also just give you this one thing. Suppose this is A and this is B. So this is clearly a rectangle. So the displacement will be AV. Okay. This is constant acceleration. Now V proportional to T. So obviously A will be constant. To differentiate it, we'll find out. So the area under this line will give the displacement. Again, due to the same reason. Okay. Also this will be also the same. This is just negative, but it doesn't matter. Probably the displacement will come negative. Okay. Now this is non-uniform acceleration. Why? What is non-uniform acceleration? That is non-uniform velocity. That is acceleration present. And this is non-uniform acceleration, which means this is the VT graph. The acceleration and the graph is like this. Now, the slope of the VT graph gives acceleration, right? So, the tangent here is like this. This has one slope. The tangent here is like this. This has another slope. The tangent here is like this. This has also another slope. Or if it is like this, at this point the slope is 1. At this point the slope is another. Again, this slope is also different. So, the A is not constant. A is changing, which makes it non-uniform. Non-uniform acceleration. Okay, the slope, that is dv by dt, is changing at each point, which means the acceleration is also changing at each point. So the acceleration is non-uniform. Now for motion under gravity also, when we did the ball throwing thing, the projectile thing, we can also draw the graphs of those. This is the projectile motion. Now, as you can see, the path is basically curved, it's parabolic, obviously. So, x is proportional to t square. Okay, first of all, this is, so you can see this, clearly visualize it. Now, the velocity. If you see what happens is, the u is initial velocity. Now the u keeps on decreasing till it becomes 0, and then it keeps on increasing till it becomes u, but in opposite direction. The graph of it, when you see it, it may seem out of the blue. I'll explain it to you here. The graph is like this. Okay, or just like this. Now, how is that? This is the velocity time graph. Okay. It starts with a velocity u. It is thrown with a velocity u, obviously. Now it decreases. It decreases. It is decreasing. This line is decreasing. This is decreasing. And it reaches a point where the velocity here, the y-axis is 0, y-axis is velocity. So the velocity becomes 0. Like in here, the velocity becomes 0. And then it starts increasing, but in the opposite direction, in the negative direction. Suppose this direction was positive. So it starts increasing in the negative direction. Now the velocity is increasing. The y-axis is increasing. The y-axis is increasing, right? But in the negative direction. So this is the graph for projectile until it reaches u. This is minus u, minus u. This is plus u. So this is the graph of a projectile. Okay, or motion under gravity. So now we have reached the end of the chapter, that is relative velocity. And we define relative velocity as like seeing the velocity of another body from the perspective of one body. Okay, suppose there's a body A and there's a body B. They're moving with velocities. Suppose VA and VB. So the relative velocity is suppose VA with respect to VB. Okay, or VB with respect to VA. These are called relative velocities. And these are defined by VAB means V of A with respect to B, with respect to velocity of V, which is nothing but VA minus VB. Okay. Similarly for B, if it is B velocity of B with respect to A, this is velocity of B respect to velocity of A. This is nothing but VB minus VA. VBA is just VB minus VA. VAB is VA minus VB. The one in front minus the one in back. Okay. Also, in practical knowledge, what does with respect to mean? This is with respect to. What does this mean? Velocity of A with respect to velocity of B. That is velocity of A, how B sees it. What is the velocity of B? What is the velocity of A from the perspective of B? Similarly, velocity of B with respect to A is velocity of B with respect to A. That is how A sees it. What is the velocity of B from the point of view of A? From POV of VA or A. This is why, and this is nothing, just with respect to means just subtract them. Okay, velocity of AB, A with respect to B is velocity of A minus velocity of B. Okay. Now in the start of the chapter, you may have remembered that we talked about how rest and motion are not absolute. And why is that? Because you were sitting here and you were seeing two trains moving, suppose with the same velocity vt, that is velocity of train, and your velocity of man, this is velocity of man, which is 0 because you are at rest. Now, velocity of the train with respect to man, velocity of train with respect to you, that is man, that is vt minus vm. Now vt is vt, and what is vm? That is 0. So the answer is vt. So the train will have some sort of velocity from your perspective. Now for a person sitting in this train, watching this train, you will see this as, suppose velocity of train 1 with respect to train 2, it is vt minus vt, which is 0. Because they're traveling in the same direction, we take it as like positive, both positive. So basically 0. So that is why when you are traveling in a train and you see another train parallel to you, you see that it may seem that the other train is at rest. Why? Because if you're going at the same velocities, the relative velocity, the velocity of the other train from your point of view is 0. That's why it appears at rest. This is a kind of pseudo concept because the train is actually moving. It seems like it is at rest. Similarly, if you take other examples, like suppose a body A is moving with velocity 10 meter per second. Body B is moving with velocity, suppose 8 meter per second. Now, what is velocity of A with respect to B? That is VA minus VB equal to 10 minus 8 equal to 2 meter per second. Velocity of A with respect to B. So B sees A coming with 2 meter per second. Okay, this is the illusion. A is coming with 10 meter per second, but B sees A coming with 2 meter per second. Now, if the similar case was here, but the direction is reversed. That is, B is now coming towards A with 8 meter per second. Now, suppose we take this direction, the right direction as positive and the left direction as negative. Okay, so what is VAB? That is VA minus VB, right? So it is 10 meters because it's going in this direction, so the 10 is positive. But eight meter is going in the direction which we have taken negative. So 8 meter would be minus 8 meter per second. Velocity would be minus 8. So it is minus, the minus will be same, but the velocity of B will be minus 8, which is 18 meter per second. So A is coming, velocity of A originally is 10 meter per second. But B sees it, that is velocity of A with respect to B with 18 meter per second. This is why when we run towards moving objects, the object seems to come at us at a faster rate. Okay, I'll just explain it again that B is coming with 10 meter per second in reality, but to B it seems it's coming with 18 meter per second. This is basically what relative velocity is. Now there's a last application of relative velocity, that is crossing of train. So suppose there are two trains. Suppose this is one train, and this is another train. Suppose this train is B, this train is A. They have lengths LB, LA, and going with velocity VB and VA in the same direction. Okay. So now first we have to understand what does crossing over means. And this is the top view, okay? Suppose you're watching two trains from the top. So I'll just erase these for convenience. Suppose this train was here. This is LA. So first, this train A would have to cross its entire length LA to become parallel to B. So the train is traveling complete LA length to become parallel to B. Now, when it has become parallel to B, it has to travel this entire length. Suppose this is, I'll just overlap them for making you understand better. That if you overlap them, the train A has to completely travel the distance LB also to finally cross this train A. So I'll just tell you again. That is, this train A was here, suppose. It travels the complete distance LA to become parallel to B, and it travels the complete distance of the train B, that is LB, to finally cross it. So the total distance here traveled by this B, and we have kept B fixed here, we are making A travel. The total distance here is LA plus LB. Okay, now if someone tells you find time for crossing or time for A to cross B, you can easily say that what is time, that is we can be equal to x or L, the length, by time. So time is length by velocity. Okay, so time equal to length. What is the total length traveled by A? That is LA plus LB. And what is the velocity? Now, here, when we are finding the distance traveled by A with respect to B, technically we're finding that no, that if we keep B fixed with respect to B, how much distance has A traveled? So that is LA plus LB. Now we have to take the velocity also relative. Why? Because we are seeing the velocity of A with respect to B from the perspective of B. How much velocity, with how much velocity A had crossed the distance LA plus LB. So the velocity will be VA minus VB. So it is VA minus VB. So basically it's the L relative by V relative. This is basically time of crossing. Reach the end of the chapter and we'll solve some questions here. It is a numerical ratio of average velocity to the average speed. So basically, speed, the magnitude of speed was always lesser than equal to the magnitude of velocity. Similarly, for average speed, it is similar, greater than or equal to average velocity. If we take the ratio of average velocity by average speed, it is always less than or equal to 1 because the numerator is smaller than the denominator or equal to the denominator, always. It's like either 3 or 3 by 5. The numerator is smaller than the denominator, which makes it less than 1. Okay, so the answer is this. In 1 second, a particle goes from point A to point B in a semicircle shown in the given figure. The magnitude of average velocity. Figure is not given here, but suppose this is the semicircle, this is the point A, this is the point B, and the circle has a radius 1 meter. Okay, now the boy starts from here, goes all the way with this path and reaches B. Now this is asked velocity, rather average velocity. So we have to find the displacement, not the distance. So the displacement or the path length between the initial and final position, that is this. Now in a semicircle, the distance between these 2 points is called the diameter. Diameter is twice of the radius. This is d, which is twice of the radius. You have to have some sort of geometrical knowledge here. And I've already told that the radius is 1 meter, so the displacement is 2 meter. The diameter is 2 meter and the displacement is 2 meter. So the average velocity is displacement by time, that is 2 meter by 1 second, that is 2 meter per second. This is the average velocity. This is a tough question, we'll come to it later. There are some really good questions here. So if the displacement of a body varies with the square of elapsed time, then it is x proportional to t square. Write it out clearly. Now, let's assume some value for easier calculation, suppose 2t square. Now, the velocity is constant. Differentiate the position with respect to time, velocity becomes 4t. So definitely it's not constant, it is variable. Velocity varies non-uniformly. No, because the velocity is linear with t. So it is straight line, it forms a straight line. So the slope is same. So it just varies uniformly because the slope is same everywhere. So this option is also wrong. Acceleration is constant. Differentiate this with respect to time, which gives a equal to 4, which makes it constant. So this option is correct. The acceleration changes continuously, that is variable acceleration, which is false as we have seen in here. The area of acceleration displacement curve of a body gives, now this is a question out of your syllabus, but this is a really good question. If you know the formula of work, you can apply this. Basically, area, acceleration, displacement curve. Suppose this is a random curve, area is a dot x, which means suppose f by m dot x. Now f dot x equal to work, and this is mass. So work by mass can also be told as kinetic energy by mass, which is change in kinetic energy per unit mass. Completely optional, not studied yet. If you know the formula of work, well and good. You just have to play with units. And that's it. A body moves in a straight line for some time and then returns to the starting point. If the total time taken by the body to complete this path is 20 seconds and the total distance traveled by the body is 40 meters, which of the statements is incorrect regarding the motion of the ball? Also, the incorrect option is true. So please don't confuse it with, like, don't mark the opposite options. Don't mark the correct options. Body moves in a straight line for some time and then returns to the starting point. Drawing diagrams is really helpful. So the moves in a straight line and just returns to the starting point. Okay. Total time taken is the displacement of the body is 20 meters. 100% false because it returns to the same point, means the displacement is 0 as the initial and final point are same. The displacement of a body is 0. This is correct. The average speed of the body is 2 meters per second. Now the total distance traveled is 40 meters. Total distance traveled is 40 meters and the time taken for it is 20 seconds, right? So it is 2 meters per second. This is true. Average velocity of the body is 0. 2. Because the displacement is 0. It's 0 by 20, that is 0 meters per second. So this is the correct option as this is the incorrect option. Okay. This one's really nice also. Keep this deepen. Which of the following velocity time graph shows a realistic situation for the body in motion? Now, if you see this is also a tough one. If you see this, the first one, and draw a line here, you can see at this point, at this point, at this point, it is the same velocity. No, sorry, at the same time, this has three different velocities. So the y-axis is the same, that is t, suppose, at t seconds, but the x-axis is the same, that is t seconds, but the y-axis changes continuously. That is, it has this velocity at this point, at this velocity at this point. So what does this basically mean? That at a single time frame, that is t seconds, a body has simultaneously three velocities. Suppose this is v3, v2 and v1, which is not possible, right? A body cannot have three types of velocities in just 1 second, right? So this is false. Now this is velocity. This is plausible because the velocity is increasing first, then it's decreasing, then again it's increasing. This can be a possible option. Again here, suppose at this time frame, suppose at the coordinate at time t seconds, velocity has three velocities at the same time. So it is completely false. Again here also, body has two velocities at the same time, here and here. Suppose at t1 it has two velocities, t2 it has two velocities, t3 it has two velocities. This is false. The only correct option is this one. Hope you understood this. Sorry. So body, it may look difficult, this one, but it is very easy. Just basic differentiation. The body of mass m moves along x-axis such that the time t and its position is x equal to, this is the equation is given, alpha, beta, gamma are constants. You were taking 2, 3, 4 and numbers. So here alpha, beta, gamma are constants. We'll write alpha t square minus beta t cube plus gamma t. The acceleration of the body is, so first we'll just do dx by dt. That will give v, that is alpha 4 alpha t cube minus t beta t square minus gamma t. Basically these are constants, so you won't have to mend with them. Okay. So for acceleration it's dv by dt, that is a equal to 12 alpha t square minus 6 beta t minus 0, obviously, because gamma was constant and the differentiation of constant is 0. So it is 12 and this option. Option B. Okay. The displacement time graphs of two particles A and B are straight lines making 30 degree and 60 degrees respectively with their time axis. So the velocity of two particles BA and BB respectively are, so to see this, suppose this is A with 30 degree with the horizontal. This is B with 60 degree with the horizontal. Okay. This is the fresh diagram. This is the position time graph. So we have been told to find the velocity, the ratio of velocity of A with velocity of B. Now, how to find that? That is, if you find the slope of the displacement and time graph, it gives you velocity, right? It can also be written as dx by dt or tan theta. So VA by VB equal to tan 30 by tan 60. Okay. So tan 30 is 1 by root 3, tan 60 is root 3 equal to 1 by 3, which is this option. So I guess these questions are finished, just that one question is there, which is, I'm sorry, find it. Yeah, this one. So particle covers half its total distance with speed v1 and the half distance with speed v2. Its average speed during the complete journey. What is average speed? Total distance by total time. Now in questions like this, it's better if you draw a diagram. Okay. Suppose he is going a total of 2s distance, or you can just take total distance here is s. So this is s by 2. This is again s by 2. So the particle covers half of its total distance, that is s by 2, if the full distance is s, with speed v1, and the other half with speed v2. Also, we can, for convenience, if we assume that the whole path length is 2s, we can divide it as s and s, which is more convenient. So we'll take this. So the average speed equal to total distance by total time. Now, this is L by T. Or rather, suppose this is T1, this is T2, which is to cover S2 with V1 speed, it takes T1 time. To cover V2, or to cover S2, or the other half with V2 speed, it takes T2 time. Okay. So the total distance is S plus S, that is 2S. We have already discussed this. We have taken this as a convention. That is, total time takes is T1 plus T2. Okay. Now what is T1? T1 we can write as distance by velocity, or from the start, velocity equal to distance by time, right? We can write T1 as distance by velocity, that is S by E1. Okay, for this graph, not this one. Time T2, I'll just erase this bit. So time T2 equal to similarly S by V2. S distance, to cover S distance with V1 time, V1 velocity, T1 time is taken. To cover the other half, that is another S, with V2 speed, T2 time is taken. So T1 by T2 is the total time. Velocity equal to distance by time. Time equal to distance by velocity, that is T1 equal to S by V1, as in here, and T2 equal to S by V2. So just put the values in here. 2S S by V1 plus S by V2. 2S S by V1 plus S by V2 equal to 2S. Just take S in common. It is 1 by V1 plus 1 by V2. S gets cut here. So it's 2 V1 plus V2 by V1 V2 equal to, the answer becomes 2 V1 V2 by V1 by V2. This is our final answer. Okay. That is this one. This may seem a little tough, but this is just very simple maths. If you took the total distance as S and the half distances as S by 2 with V1 and T1, V2 and T2, it would be the same thing, just it would be S, because S by 2 plus S by 2, that is, and T1 would be this. T1 would be distance by velocity, that is S by 2 by V1 plus S by 2 by V2 for T2 into S by 2 V1 plus S by 2 V2. Now just take in common. By V2, these two get cut. 1 by half V1 plus V2, V1 V2. Just solve this, and again the answer is same here. This is the same answer. So this is the end of the chapter. I hope you have